Then, hello everybody and welcome to this week's JINA online seminar. It's a pleasure to announce the speaker of the day, who is James Keegans from the University of Hull in the UK. So it's our first intercontinental JINA seminar. And he will tell us about post-processing of multidimensional supernova models. So please go ahead whenever you're ready.
Okay, thanks, Ingo. Thanks for asking me to speak. And I'll just quickly go through sort of the main points that I want to talk about today. We're going to talk about supernova very briefly and their role in JINA-CEE, the types of mechanisms and the current models that we have. I'll talk very briefly about post-processing. I'm sure a lot of you will be very familiar with it. And then I'll move on to talking about my current work, which is mainly so far been benchmarking to make sure that the things that we're doing are correct. But I've also had a look at sort of metallicity dependency and trying to reproduce some results from some papers. And then I'll talk briefly about future work, sensitivity studies, which we think are very realistic and probably not too far away, full yield sets, which may take a little bit longer, and then error bars for yields, which is quite an exciting prospect. Not entirely sure what the results of those will be as of yet. So yes, moving on to the role of supernova in JINA-CEE. I'll talk briefly about the sort of proportion of single to double degenerate, what's the difference between single and double degenerate scenarios, what evidence have we got for supporting them either way. Yes, supernova can contribute across a wide mass range, so 0.8 to 8 solar masses. Type 1a does not go all the way up to 8 solar masses, and you run into electron capture supernova just before, but the upper boundary of that is somewhat uncertain. So I've put it here as 8 solar masses. 8 to 100, of course, is a core collapse supernova, and they produce a whole range of material, the alpha elements and ion group elements. Type 1a supernova mainly contribute ion group elements and to a lesser extent some of the alpha elements there, like silicon and sulfur. Production of the ion group elements has been by type 1a supernova has been investigated thoroughly over a long period of time. It's very important for JINA-CEE models. There are a whole slew of effects that can impact the yields that you get. So, for instance, metallicity is one that is often investigated. Got Timmers here, 2003, Travaglio, 2005. This impacts the mass of nickel 56 that you eject from your supernova, and therefore, of course, affects the light curve that you have. So, important consideration there for distance scale, standard candles, and things such as that. Something that I find particularly interesting, although it's not a primary concern for the JINA-CEE community, as far as I understand it, is p-process nuclei in supernova 1a. So there has been some work, Travaglio there, 2015. You can see the plot. The solid points are all of the 35 classical P nuclei, and you can see that a lot of them are produced here, overproduced in type 1a supernova. But as I say, because the abundance of them is much lower than that of say, for instance, S or R process. Yes.
I cannot see your cursor or anything moving around. So.
Oh, sorry.
Yeah. There it is. Okay, thank you.
These solid points on this plot here, Travaglio 2015, sorry. Yes, so as I was saying, the solid points, many of them are overproduced in type 1a supernova, but because of their low absolute abundance, they're not a primary concern, but I think very interesting. Moving on here, elemental ratios. So this plot from Kobayashi 2011 is very interesting. There's a lot of information here. I'll try not to spend too much time. You can see around about Fe on H. I'm not entirely sure the background of everyone. So Fe on H is, in some respects, can be thought of as a proxy for looking backwards in time. As you go to lower values of Fe1H, you go to lower metallicities in the star that you have. So -1 is a tenth of solar, -2 is 100th, and so on. Of course, this is not always the case. So in this paper, Kobayashi 2011, they do mention that some stars can be formed very early on with metallicities exceeding solar. But generally speaking, it can be used. It can be thought of for many stars as a proxy for time. So as you look back on this plot, -4 is further back in time, and moving forward to 0 sort of present day metallicity. You can see that around about -1, many of the alpha elements, neon for instance, magnesium, they take a steep downwards trend, and this is because, as I mentioned a couple of slides ago, core collapse supernova, which are massive stars, have very short lives. They burn through their fuel and they explode in the early universe and produce alpha elements and ion group elements in large amounts. And as you move forward, there's a delay time between the onset of contributions from supernova 1A and then at around about a tenth solar metallicity, you can notice for the alpha elements a decline in their abundance or relative to iron. Or in the case of the ion group elements, for some of them, for instance, nickel and manganese, you can see an increase as there's a larger contribution to these from type 1A supernova. There are two interesting points, two interesting elements here to highlight. Cobalt here seems to have no dependence on type 1A, but it's not immediately apparent from this. The reason that this is flat, this is a flat relationship here, is because 2/3 of the solar metallicity, which is what we normalize to on this plot, is produced from type 1As, and it so happens that 2/3 of cobalt is also produced from type 1As. And so although it looks as though cobalt stays flat and there's no further production of it, it's just because iron production is increased in the same proportion as cobalt. Another interesting one is copper here. It seems as though copper is produced more in type 1A than many of the other ion group elements. But in fact, most of the copper that you see that causes this increase, you can see the increase starts well before -1 as well, is due to AGB stars. So those are two interesting features of this plot, in addition to the already interesting features that, I mean, it's a pretty cool plot. Yeah, I think this is this page. So moving on, talk quickly about mechanisms for type 1A. The double degenerate scenario is thought of as two compact object white dwarfs coalescing, and by that they exceed the Chandrasekhar mass. Electron degeneracy can no longer support their weight, and so they implode and then they explode. And this is the idea that supernova type 1A are produced by this coalescing of two compact objects. There's some good supporting evidence for this. So we do not see any hydrogen lines, which you would not from a carbon-oxygen white dwarf. Observations of binary white dwarfs show that around between 1 and 20% of white dwarfs are in white dwarf binary systems. And so that seems a good proportion, a high enough proportion for us to produce the requisite number of type 1A explosions. And the birth rate of the progenitors is the best fit of any scenario. So the double degenerate scenario has some strong supporting evidence. However, there are some difficulties because of the nature of the distribution of masses of white dwarfs. You might expect that the distribution of the production of nickel 56 would also be different. You see, if you have two quite small mass white dwarfs, 0.8 solar masses, for instance, and then they coalesce, you would expect that you would have a very different amount of nickel 56 produced as compared to two white dwarfs at, let's say, 1.1 or 1.2. But nickel 56 production is very consistent throughout type 1As. This is why we use them as standardizable candles, obviously. And so that particular aspect doesn't quite fit with the idea that we have. Explosions of carbon option white dwarf binary systems as well are dependent on the configuration, and so you would expect that a certain proportion of these binary systems would coalesce in a different manner, and therefore they would have different explosion energies, and it doesn't seem that observations support this. But for a full review of this, Hildebrand et al. In 2013 is an excellent review paper. The mechanism for the single degenerate scenario is the model that we are investigating currently, and the single degenerate scenario is the one that I'll show you the work that we've been doing. So you have a main sequence companion which it overfills its Roche lobe and material is accreted onto the white dwarf. There's supporting evidence also for this. Manganese over iron ratio, which I can show you a few plots of in a moment, why it's particularly important that we have the single degenerate case. Manganese over iron, it's necessary to have a proportion of single degenerate type 1A progenitors in order to reproduce the manganese to iron ratio. And also observations of nickel and magnesium in this particular remnant here, 3C397. They require the presence of a single degenerate system. But unfortunately, there are also difficulties with this model. There's no clear way that a white dwarf that starts off at, let's say, for instance, 0.8 solar masses can accrete enough material without blowing it off in nova bursts to reach the chandrasekhar mass. It would take, we think, too long. Denisenkov is a very thorough paper that discusses this in some detail. And so we think that perhaps the accretion rates there are problematic. And there are only marginal statistics from observations of emission lines to support the presence of single degenerate systems. So, for example, I have made a note here. Observations in Johansson et al. 2016. They exclude high temperature single degenerate scenarios to the degree that only around 3 to 6% of type 1A supernova can be caused by the single degenerate case. So as you can see, there's difficulties with both of these models, and again, I would recommend reading, if you want a more thorough introduction to it, the Hildebrand paper. So very briefly, talk about the stages of burning. So this is Thielman, Nomoto, and Yoko in 86, and you can see there are different regions of burning for different given temperature and density. So the temperature here is the top line, and the density here given at the bottom. And so for temperatures between, let's say, 4 gigakelvin and going down to about 0.7 gigakelvin, 10 to the 7 grams per cubic centimeter, sorry, you can expect to have explosive neon and carbon burning. Alpha-rich freeze-out occurs between around 7 and 5 gigakelvin, depending on the density, and normal freeze-out, not alpha-rich, which is required for producing the more neutron-rich species, occurs at much higher temperatures and much higher densities here. And that should become a little clearer in one of the plots that I'm about to show you. And also up here, just to reinforce that, this is a second plot from the same paper that shows you density on the y-axis and temperature on the x, and it shows you the different regions under which alpha-rich freeze out, incomplete silicon burning, and so forth occur. And so we can see that different phase spaces in the type 1A supernova, depending on their peak temperature and peak density, will produce different burning regions. The difficulty here is that This plot, for example, gives a mass coordinate with our two-dimensional models that we are currently working on, and then moving towards three-dimensional ones once we have worked out all the kinks. The mass coordinate is no longer a useful tool for us to describe where the particle sits in the star. The peak temperature that a particular particle experiences will vary wildly due to the trajectory that it takes through the star during the burning. And so even though a particle may be further out, so on this plot it would be out here at quite large radii, the particle in our simulation may experience much more extreme conditions because of the 3D nature of the model. So it's not directly comparable between this plot here and our work, but hopefully the plots I'm about to show you should make that a bit clearer. So I'll briefly outline the source of our models, talk quickly about deflagration and just mention detonation, and then talk about the fluid history tracks that we have and some of the techniques that are used to clean those up. Townsley et al. Presents deflagration, detonation, transition models in 2 dimensions is the work that we have at the minute, although I believe there are 3-dimensional models ready to go and be post-processed. If I just look at my notes here, sorry, not going so well. Sorry, no. So these tracks here represent some benchmarking that has been done in this patent paper 2016 between a single dimensional model and the burning benchmark that they have. It's just here to show you some of the thermodynamic conditions that a typical tracer particle would experience. We can move on from this. Deflagration tracks in the model experience a slow burning front. It is a subsonic flame, causing the star to expand. Now, this expansion changes the rates of propagations of the flame and the burning products there. So the paper here, Koklov 91, predicts that all of the carbon should be burnt in a white dwarf, but this being a one-dimensional model, it's not particularly clear if this should be the case. And in fact, when we look at the analysis that we have for the runs that we've done, there is some carbon left, a small amount in some of the outer regions. The tracer particles presented in the plot here. The track is the temperature and progress profile for a particular particle. However, due to the method of modeling the explosion, the flame front for the deflagration has to be made artificially thick to get the required burning. But this means that the particles in that flame front spend too long under certain conditions. It means that they are unphysical. And so on this plot, you can see that the red lines are the reconstructed tracer particle trajectories, which that extracts the correct thermodynamic trajectories for a particle. It's unclear as of yet what the impact is between reconstructed and non-reconstructed trajectories. So in Townsley et al. 2016, there are small changes to the abundances, but this was not a full post-processing code. It was a smaller selection of isotopes, and so it could be that there is a significant effect on the abundances made by changing the particle from the reconstructed, from the non-reconstructed to the reconstructed particle set. And so as a good practice, it's our plan to use the fully reconstructed particle sets in order to be sure that what we're producing is the best that it can be. So I hope that explains a little bit about the models that we're using and the methods that are used to produce them. And now I'm going to move on to some of the work that I've done in benchmarking, looking at the metallicity dependency of the models and showing mass fraction versus maximum temperature and maximum density. So a quick word on the UGrid suite of codes that we have. There are a number of different frameworks that we use to investigate different burning in different regimes. So for instance, here are the drivers square on the right-hand side, outlines 3 different frameworks that we have. PPN is used for single zone, single trajectory analysis. So if you have, for instance, a trajectory that you're very interested in that is representative of a particular burning regime in, for instance, a type 1a supernova, if you find that you can take a trajectory out and it be representative of a larger number of trajectories, you could use PPN to produce sensitivity studies or similar in that respect. The MPPNP multi-zone post-processing network is a parallel network, and it includes mixing, and this is for things like AGB stars, where it's important that material is mixed properly between different zones for you to get the correct burning there. And TPPNP, which is the newest one, is the one that I've been working with, and it's been developed by Sam Jones, is a parallelized single zone framework whereby we can take the very large numbers of particles that we need to follow the nuclear synthesis in a type 1a supernova. So for the models that I've been looking at, we've had 10 to the 5 particles, tracer particles. When we move to 3D models, we may well need of the order of 10 to the 6 or 10 to the 7, depending on when yields are converged for those models. So TPPNP allows you to take particles which do not exchange mass between them and run them in parallel so that these problems become tractable. The physics package that we have takes a reaction network of 5,600 isotopes at its largest, although for most of the stuff that we do, because we don't have seed nuclei, we will not need to have the full 5,600 isotope network. But it also uses reaction rate libraries such as JINA-CEE, Keegans, NACA. I'm sure you are familiar with these. There's a 75,000 reaction rates that we use in this reaction in this physics package, and together with our new solver methods, we've moved currently to using better solver methods for solving our reaction network. We hope that it's a very accurate and very reliable method of post-processing. And the facility that we use, because we've got so many particles, because it's so computationally intensive, although I'm sure some of you will have other things far more computationally intensive than this, people actually producing the 3D supernova models, for instance. We have this facility in Hull. Viper has over 5,500 cores, 500 terabytes of storage, and MPI to post-process to make parallel jobs. It's very heavily used here. We've got quite a good computational group in our department, and it just makes all of this work possible. So 2D models data analysis, as I've mentioned, I won't go over it again. Mass coordinate is not useful for us. We therefore need to describe the nuclear synthesis in particles with respect to a different quantity consistent throughout the data set. And what we have chosen as our first run is the peak temperature. So the peak temperature that the particle experiences, we have chosen to be the thing that we're looking at and see how does this affect the yields. And this plot here, this is for the 10 to the 5 tracer particles, as I've mentioned. Zero metallicity, deflagration, decimation, transition, single degenerate model. And you can see that, so let's point out some features here. This dip here in the carbon 12 shows that this is the explosive carbon burning region. So the particles it's not immediately clear from this plot whether or not there is a particular region in the supernova that undergoes explosive carbon burning, but it can be said that in this plot, for these particles, they undergo conditions that are equivalent to explosive carbon burning in a different scenario. We have up here silicon-28 and sulfur-32, and you can see quite clearly they are sort of bifurcated here. They have two pathways to the same abundances up here, and so we think that this is probably due to the not only the temperature dependency, which is shown on this plot, but the density dependency as well. Different particles at slightly different temperatures will experience will have similar production because of the difference in the density. And then you can see here that nickel 56 from around about 4 gigakelvin moving into NSE becomes by far and away the most abundant of the isotopes, treading off here as we get to higher temperatures, with nickel 58 taking over here. And then we have, for instance, titanium 44, a clear peak here that has some parallels with there's another lab that's working on a PhD and has shown me his plots where the titanium abundance peak sits at 3 gigakelvin for core collapse, so that's quite interesting. So moving on from this, what I thought it would be nice, an interesting and informative thing to do would be to take the tracer particles and plot them in T-row space. So you can see there's a large density of particles here at relatively low densities and quite low temperatures as well, only about 6 gigakelvin, which of course is very high, but not the more extreme end over here. So you can see the full phase space here for the particles in the model. And then if we take these particles and rather than just colouring them to show that they're there, colour them with the mass fraction of a particular isotope, we can see the distribution of the isotope as it's produced in the particles in the supernova model. This is cobalt-55, which is the main progenitor of manganese-55. As I've mentioned before, manganese is of course one of the main indicators that type 1a single degenerate scenario models have to be a contributor to JINA-CEE, and you can see very clearly why this is the case, that there is a band of production here at around about 4 to 5 gigakelvin across a wide range of densities, which only corresponds to about a mass fraction of 10 to the minus 3, pushing to 10 to the minus 4, whereas this band here, although smaller in extent, has clearly a much higher mass fraction, up nearly I would say, from the colour plot, around about a tenth of the total mass fraction. So you can see here that cobalt-55 is very preferentially produced in much higher density and higher temperature scenarios, and these states are not populated in the double degenerate scenario. You can see here, Seitzenhaler et al., their models that show manganese over iron are greater than 0 are the only models that are near the Chandrasekhar mass. So this seems to be fairly clear evidence that in order for you to produce manganese 55 or manganese 55, which is the main component of manganese, the single degenerate model is fairly necessary. Moving on from this now, I will mention briefly that the reason that it has to be such high density, if you remember the work 99 MA2, I believe, the higher densities make us move away from the alpha-rich freeze-out to the normal freeze-out, and that is what allows us to produce the cobalt-55. So moving on, we have nickel-56 and 58, and you can see that nickel-56 is preferentially produced at higher densities and temperatures, whereas nickel-56 is you can see it's produced over basically the whole range of temperature density profiles there, apart from the much lower temperature ones here and here. We can move on to have a look at titanium-44. You can see there seems to be two distinct regions that titanium-44 is produced in. One at a slightly higher temperature at a lower density, and one at a slightly lower temperature at high density. And calcium-40 here seems to have be produced at a lower temperature but across a wide range of densities here. You can see, perhaps if I go back just slightly, you can see much more clearly here that calcium 44 is produced in this lower region, titanium, nickel 56 is produced in the higher region there. So it's quite an informative plot. And then moving on, lastly, for the last of the isotopes that were in that initial peak temperature diagram, you can see that silicon 32 silicon 38 and sulfur 32, being much lighter, are only produced in significant abundances in those trajectories that are much milder compared to the rest of them. Right, where are we? 5 minutes. Excellent. These are integrated isotopic distributions. In the top panel, we have the undecayed abundances, and in the bottom panel, we have the decayed abundances. You can see that it goes from carbon all the way up to cobalt there, just at the edge. And what is particularly interesting to my mind here is the split between the lower mass and the iron group elements. So if we take, for instance, iron, in the undecayed abundances, iron has a mass fraction of around 10 to the minus 2. And if we then look, sorry, I keep forgetting I should point. And if we then look here, iron has a mass fraction closer to 1, in fact. And this is because a large proportion of the iron that is produced in the type 1A supernova is produced as radiogenic precursor isotopes, which then decay to iron. Whereas you can see that the abundances for silicon, for sulfur, for argon, for calcium are fairly consistent between the two models, and that is because these elements are produced mainly as stable isotopes, and so that the production of those is not dependent on then. It would be better to say that to follow the JINA-CEE for those, it was not then necessary as such to follow to allow for decays, if you see what I mean. Moving on here, we have the integrated elemental abundances for different elements again, and you can see quite clearly between the two models here, distribution undecayed and distribution decayed, that the mass of ions increases significantly between decayed and undecayed, whereas for things like sulfur and chlorine, the further step of taking decayed isotopes is not a huge effect on the abundances of those isotopes. Yes, so as a benchmarking exercise primarily, but also moving on and looking at nickel 56 to 58 ratios as a possible further work, we initially ran some models to look at the effect on nickel 56 production when varying the initial neon 22 content of our unburnt material. Now, this is not a particularly intelligent way to do it, because by introducing this neon by fiat, essentially, without running the pre-supernova models, we can't be sure about the effect on burning and the flame speed and density compactness in the white dwarf progenitor to the supernova. However, as a first pass, because other published work has shown that the effects on, for instance, flame dynamics of changing neon 22 content is minimal, we thought it was reasonable to investigate this work just as a first pass. Now, I'm sure you're thinking these two plots look nothing alike. There is a very good reason for this. When I did my run, I looked at the current solar value of solar metallicity, and I found that it was quite recently it has changed to 0.0165. When this paper was produced, solar metallicity was 0.02, and so the graph on the right here actually starts at the edge of this red box, and so the variation, the 25% variation that was found by Timmers in 2003, we don't actually investigate further than here on this plot here. But taking these mass fractions and multiplying through by the mass of our system, we do find a variation of around about 4% between zero metallicity. Between zero metallicity and 0.02, which is consistent with the variation here on this plateau between the low metallicity here and the solar metallicity at the time. So unfortunately, it doesn't show exactly what I wanted to, but our hope is in the coming couple of weeks to run further models that go up to 0.2 mass fraction of neon-22 in order to reproduce these results here, and hopefully it'll be much clearer then that our models are correct. So moving on here, nickel to iron and manganese to iron, as a benchmark on supernova ejector. Although I do realise that I have talked for too long, so perhaps it is best to skip this. I will talk very briefly.
So it's fine. You can talk 5 more minutes. It's no problem. So
okay, I do have quite a lot of slides anyway, so I may just skip it anyway, and then okay. So the effect of progenitor neon-22 content on dynamics, as I mentioned earlier, because we changed the neon-22 content after the models are produced, the compactness of our white dwarfs are not correct. Work by Townsley in 2009 suggests that there's no significant effect on the dynamics of the star or the mass of the NSE material produced. But as you can see between these two plots, there is certainly an effect on the morphology of the models, right? There is some effect here, but there's no significant change in the compactness and so on. So the main concern is that the flame speed in the DDT models, the deflagration destination transition models, varies by 30% when you change the neon mass fraction, and this could have significant effects on the nuclear synthesis. So the plots that I've just shown to you with the neon-22 mass fraction versus the nickel-56, in order for those to be robust, I would need a suite of models of the three-dimensional supernova explosion, and also the progenitor to the white dwarf. So, but it seems as though that is a reasonable, interesting, and worthwhile thing to do, and so I'm going to be pressing for that to happen. Very briefly, I did want to talk about core collapse as well, but unfortunately, I will run out of time. So multidimensional models from Fryer et al. Are 10, 15, 20, and 25 solar masses. Currently, the results that we have for these are quite low resolutions. They only have about 1,000 particles. But the idea there is as a benchmark for tools and tests of explosive yields and uncertainties, and that resolution can, I'm sure, be increased should we want to move forward with producing yields for core collapse as well. So this is a plot from Andrews et al. In 2017, and you can see that there's here shown the effect of increasing the nuclear reaction network. You can see that the abundances of a large number of low mass elements is significantly influenced there. Future work, I said very briefly, I've only got a minute. Benchmarking, we'll continue to do this. Metallicity dependency, also continue working on that. And then the mass fraction versus Cmax and zero. But our real goal, in one respect, is to have resolved yields with reduced particle numbers such that we can produce them effectively using the best use of resources here at Hull, and with the greatest accuracy that we can manage, and also have yield productions with error bars, which is something I think that has not been done before, and something that Massive Advisor Marco is very keen on having, to give an idea of where the largest errors are for these models? Where can we really focus in on? Is it nuclear physics that we have to focus in on, or is it the models that we have? Where is it that we can improve these? Sensitivity studies as well. JINA-CEE is a tool that we have to investigate the impact that different reaction rates have on abundances, and so Bravo and Martin has been have identified these influential reactions in type 1a supernova, but these are extracted from one-dimensional models, and so it is perhaps useful to go back to these in a fully three-dimensional model and investigate which of these reaction rates are most important, and what is the best use of a experimental physicist's time. Which reaction rate should they be looking at? And I think reducing computational cost. I'm sure you're familiar with wanting to make things as efficient as possible, but I perhaps don't need to go through this. My conclusions: benchmark. The work against existing literature seems to have been fairly successful. Moving forward, we want to post-process 3D models, review constructed trajectories, begin work on sensitivity studies by selecting representative trajectories from the full data set rather than running for the whole data set, which is sort of prohibitively expensive. And the error bars for yields, which are in the first stages of development, but should be quite impactful. So thanks for listening. I hope I didn't send anyone to sleep.
Okay, let's thank James. And if you have any questions, please send me a note in the chat and let me know. Okay, so maybe I start. I have a question. It's regarding, there are two scenarios, right?
Yes.
So is it an either-or situation, or can it be both scenarios that work together, or how is the situation?
So I believe that the current state of thinking for most of the community is that there has to be a contribution from both single degenerate and double degenerate models, because, well, you can see, right, the two excluding factors that say, oh, this one can be and this one can't, these are quite strong constraints that we have, that we've got no accretion models that support white dwarf single degenerate ones, and that we have this uniformity of nickel 56 that we've observed. So it's got to be that there are contributions from both double degenerate and single degenerate scenarios. And I've heard some people, so I asked Brad here in the department, and for JINA-CEE purposes, I believe certainly in the last decade or so, the practices had been just single degenerate. That was the one that was the most favoured at the time. And now, going to conferences, people seem to think that a proportion of single degenerate type 1a progenitors of around about 30%, 30 to 50% is what we require to fit the manganese observations, and also to the limit on what we can allow from what we know of the type 1as that we observe.
Okay, thank you. And then I have another maybe stupid question. You showed, I think, in a few slides forward from this one, you had some plot, and on the y-axis it said progress, and I wanted to ask what progress. How do you define? I mean, what? Yeah, there it was. For instance, what is progress?
Right. Yes. So this is, I think, just a proxy for the distance travelled by the particle from a starting point, I believe. I would have to check Townsley 2016 again just to be sure, because my real area is the post-processing side rather than the modelling. But I think that's just like a distance measure.
Okay, thank you. Are there any other questions? If you have any question, just go ahead and ask. If not, let's thank James again. And then see you all for